Okay, welcome everyone to another video lecture series for integral calculus, and this video lecture series would serve as our last discussion for the summer classes. So we have the final technique for integration that is presented here, particularly on partial fractions. Okay, so I'll just be illustrating two examples for this particular topic. Okay, so just to illustrate how do we perform the method of partial fractions before we perform the actual integration of the function within our integrand. Okay, so let's have example number 1. Okay, so we have the integral of x plus 7 over x squared minus x minus 6 dx. Okay, so the idea of partial fractions is to express your given integrand into linear factors or quadratic factors. In the case of, for example number 1, you have to realize that the denominator here, x squared minus 6 minus x, is factorable into linear expression, particularly x squared minus 6 minus x minus 6 can be factored into x minus 3 and x plus 2. Now, of course, x minus 3 and x plus 2 are linear factors. Now, in the first step of performing partial fraction, the first step, once you have factored out once you have done the factoring of your denominator, the next thing to do is to separate your fraction into the number of terms into separate fractions or individual fractions corresponding to the individual denominators, which are the distinct linear terms in the factors that were obtained from factoring your denominator. So since you have two linear factors as the factors of our denominator x squared minus 6 minus x minus 6, therefore if we're going to separate this whole fraction into two fractions, each of which would have its own distinct linear factor as its denominator. Okay, so now what we do is what we have done here is that we have separated our integrand into two fractions, having each of the denominator as the distinct factor of the factors of our original denominator, and the numerator corresponds to generic symbols that would represent the value of its numerator. Now, normally we just assign any letter, so we have A and B and so on. Now, of course, if you're going to add the two fractions here, we would end up with the sum of the fractions in which we obtain the original denominator as our given integrand. So essentially, by equating these two, since these two are equal, essentially we take note that x plus 7, which is the numerator of our integrand, is essentially equal to this expression above. So take note that x plus 7 is equal to a x times x plus 2 plus b times x minus 3. Of course, what we have obtained here is the sum of the two fractions that were the representation of your partial fraction in the initial step. Okay, now I will be cutting the solution for the integral here, and we will just be focusing more on how to obtain the values of a and b, because this would actually be our main objective before we perform the process of integrating the resulting integrand. Okay, so the idea is to solve for a and b, which would eventually represent our partial fraction. Okay, so there are actually two methods in solving for a and b, or the numerators that corresponds to our partial fraction. So I'll be presenting both methods. Okay, so we have the first method. The first method is simply that you choose a convenient value for x so as to solve for any of the values a and b. So taking a look at our given expression, x plus 7 is equal to a times x plus 2 plus b times x minus 3. So essentially what we want to do is to eliminate one of the unknowns, eliminating one of the unknowns and solving for the other unknown. So of course, if we're going to if we want to solve for a first, that means this expression on the expression of b should be somehow be equal to 0. So doing that, since we realize that if we're going to assign a value for x as equal to 3, remember this method is you have to choose a convenient value for x. Now, of course, a convenient value for x in such a way that this expression for b becomes 0 is to choose that x should be equal to 3. Now, if we're going to substitute the value of 3 in our expression, this becomes 3 plus 7 equals a times 3 plus 2 plus b times 3 minus 3. Of course, this already becomes 0, and what is left in our expression is that this becomes 10, this becomes a times 5. Solving for a, that becomes 10 over 5, a is equal to 2. Now, we have conveniently solved for a. Now, doing the same for the solution for solving for b, looking back again at our given expression. Of course, since the coefficient representing your expression for a consists of x plus 2, so a convenient value for x that we should assign here in such a way that we could cancel this and making this expression equal to 0, and leaving behind an expression for b is that x should be equal to negative 2, so that we have negative 2 plus 2 that equates to 0. Okay, so if we assign x equal to negative 2, that becomes negative 2 plus 7 is equal to a times negative 2 plus 2 plus b negative 2 negative 3. Of course, this expression for a already becomes 0, and this becomes 7 minus 2, that is equal to 5, while b times negative 2 minus 3 becomes negative 5. Solving for b equals negative 1. Okay, so that is the presentation of the first method, choosing a convenient value for x, then solving for a and b. Now, we have another method of solving for a and b, so I'll be presenting this also. So the second method is by using equating coefficients to solve for the coefficient a or b. Now, let's go back to our original expression. X plus 7 is equal to a times x plus 2 plus b times x minus 3. Essentially, what we can do is to distribute a to the expression x plus 2 and distribute b to the expression x minus 3. So doing that, we will have this resulting expression. So from here, notice that we can group together ax and bx and factor out x, so that we can have a group for x, and the remaining terms in our expressions could serve as another group. So doing that, we have x plus 7 is equal to x times a plus b, plus the group of the other remaining expression, we have 2a minus 3b. So essentially, if you're going to look at the right hand side and the left hand side of this equality, by equating coefficient, this would serve as a plus b serves as an equal coefficient for the coefficient of x here on the left hand side of the equal sign. Since obviously the coefficient of x here is equal to 1, so essentially that is 1 is equal to a plus b. Now, also by equating coefficients, 7 here serves as a constant that is added to x, and that serves as an equal coefficient for the remainder of the expression on the right hand side of the equation. So this means 7 is equal to 2a minus 3b. we call this process or we call this method equating coefficients. Now, from the resulting method, we arrive with the following expression. We have 1 is equal to a plus b, and 7 is equal to 2a minus 3b. From here, we could make use of solution to linear equations. You could either use elimination, substitution, simultaneous equation, whichever is preferable, so that you can solve for either A or B. So what is presented here is that I made use of our representation from the first equation, solving for B. Then from here, solving for B, B is equal to 1 minus A. Now, making use of substitution, I'll be making use of this representation for B in terms of A and substitute that in the expression for the second equation on replacing B in the given equation. So we have 7 is equal to 2A minus 3 times 1 minus A. Simplifying, this would be 7 is equal to 2A, negative 3. Distributing negative 3 to the expression, we have negative 3 plus 3 times A, that gives us 3A. Now, of course, we can add 2A with 3A, so that becomes 5A. And transposing negative 3 to the other side, that becomes 7 plus 3. And dividing both sides by 5, that gives us 7 plus 3 over 5. Now, of course, 7 plus 3 is 10. 10 over 5, that gives us 2. Now, A is equal to 2. If we're going to look back at the first method, we also have solved for the same value for A. Now, continuing the solution for the second method, we made use of the representation of B in terms of A. Now, since we have already solved for A, we could substitute again the value for A in this expression, then solve for B. Now, B is equal to negative 1, just like what we have solved for using the first method. Now, of course, the idea here is that I have presented to you two methods and solving for A and B. Now, it's up to you which method would you prefer and which method would you employ. So regardless of which method, you should arrive with the same values that we have solved for A and B. Okay, so now once we have solved for A and B, we can now continue solving for our partial fraction. Remember, our given is that we have this original given expressed in partial fraction form. We have A over x minus 3 plus B over x plus 2. Since we have already solved for A and B, the next step is obviously we have to substitute the values we have solved for A and B in our given partial fraction. Now, doing that, we have our original given equal to 2 over x minus 3 minus 1 over x plus 2 dx. Now, so from here, essentially, is that we distribute the integral sign in dx to the two terms. So we have 2 integral of dx over x minus 3 minus dx over x plus 2. Now, from here, it's a simple substitution for representation for u of the given expression in our denominator, and then you just employ our usual processes of integrating du over u or dv over v. You should arrive with the form of the equation of the resulting integral as ln of x minus 3 square over x plus 2 then plus c. Now, of course, the transition from this step up to this step is that you need to employ the properties of natural logarithms or the properties of logarithms. Remember, 2 ln u becomes u square, so that becomes x minus 3 square minus x plus 2, ln of x plus 2. Of course, if you have two logarithms that are subtracted together, you can combine them in such a way that you can express them using a single logarithm, where the first expression for the logarithm becomes your numerator and the second term becomes your denominator, so that the final answer would be what you see here as our final answer. Okay, so let's have example number 2. Okay, so we have 5x squared, integral of 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. Okay, so just like what was presented in example number 1, what we can do with our denominator is to have or express our denominator into factors. So just like what was mentioned earlier, the factors could be linear factors or quadratic factors. So what we see here is that initially we could factor out the common term, which is x, so we can have that outside the expression x. Now obviously what is left here is this becomes x squared plus 2x plus 1, which can be factored further into x plus 1 then square. Now of course x plus 1 is a linear factor that is raised to an exponent or a power. Now example number 2 is quite different from example number 1 in a sense that you have linear factors for your denominator, but your denominator, which is a linear factor, is raised to a power. Now for expressing this kind of denominator into a partial fraction, what we need to do is to have separate fractions for each of the distinct denominators, factors in our denominator. So those are x and x plus 1. But since we have x plus 1 raised to a power, so for every given linear factor that has this kind of form, what the corresponding partial fraction is that we need to build up the individual partial fraction building up to the given power of that given linear factor. So how to illustrate that? Let's see how this is done. So of course we have a over x as the first distinct linear factor for x, plus b over. Now what was said earlier is that for every given linear factor that has a power, we have to express that into separate distinct linear partial fractions, starting with its base form and building up to the power of that given linear factor. So starting with its base form, which is x plus 1 plus c over x plus 1 squared. Now if it happens, for example, if this is say x plus 1 raised to 30, or say x plus 1 raised to 100, then you will be expressing the corresponding partial fraction into b over x plus 1 plus c over x plus 1 square plus d over x plus 1 cube plus e over x plus 1 raised to 4, and so on, building the corresponding partial fractions up to the power 100 if the power of x plus 1 becomes 100. Okay, so I hope that you got the whole idea here. Now before we proceed, let us go back to example number 1 and try to compare this with the given integrand in example number 2 with that of example number 1. Remember our linear factors for example number 2, we have x plus 1 square. Comparing that with our example number 1, none of the linear factors present in our example number 1 is raised to a given power. So obviously these are distinct factors, so that we could simply express the partial fractions into fractions with those distinct factors. Now the difference with example number 2 is that we have distinct linear factors, but one of the linear factors has a power. So in cases such as this one, we will be building up the corresponding partial fractions up to from its base form up to the given or the highest given power for that linear factor. Just what was illustrated earlier in this example. Now the next step is just like what we have done in example number 1, that we're going to add the corresponding partial fractions, so that we will have or we will be obtaining the original denominator. So doing that, we will have this expression, resulting expression for our numerator. So we have, of course, between x plus 1 and x plus 1 square, the least common denominator among them should be x, which times x plus 1 square, which is our original denominator. Now, of course, obtaining the expression in our numerator needs us to divide individually the corresponding denominators multiplied by their individual numerators. So doing that, we have x times x plus 1 square divided by x. That cancels out x, leaving out x plus 1 square multiplied by a. So we have, therefore we have a times x plus 1 square. Then plus our common denominator divided by x plus 1. That cancels one of the factor of x plus 1, leaving another x plus 1 as a factor, and x, multiply that with b, so that we have bx times x plus 1. Plus, we have the least common denominator divided by x plus 1 square. That would cancel x plus 1 square, leaving out x, multiplied by c, then we have c times x. Now, of course, from this expression, we need to take note that our original numerator, which is 5x squared plus 20x plus 6, should be equal to this whole expression in our resulting addition of the partial fractions. Now, so from here, well, obviously, since we have this expression as a rather complicated expression, choosing now between the first method and the second method, it is quite obviously preferable that we use the second method, or using equating coefficients to solve for the values for a, b, and c. Now, of course, in order to perform the equating coefficients and solving for a, b, and c, we need to first simplify the expression into the form of having an expression for x squared, for x, and for the constant. Okay, so doing that, we need to expand x plus 1 square into x squared plus 2x plus 1. We need to multiply bx with x plus 1, so that becomes bx squared plus bx, then plus cx. Okay, so doing the groupings, we have ax squared plus bx squared, factoring out x squared, so that becomes a plus b. Now for the x's, we have 2a plus b plus c, factoring out the common factor x. Then finally we have plus a. Now obviously this serves as the coefficient for your x squared, since they are both x squared. So that means we have 5 plus a plus b. 5 equals a plus b. Now for the coefficient of x, we have 20 is equal to 2a plus b plus c. And obviously the constant 6 is equal to the remaining expression for our right hand side of the equal sign, which is a. So obviously we already have solved for a. A is equal to 6. Now since we already solved for a, notice that we can use the first expression, 5 is equal to a plus b, to solve for b. Solving for b, b is equal to 5 minus a, 5 minus 6, that becomes b equals becomes negative 1. And finally, for as a third step, since we already solved for a and b, substituting the values we have solved for a and b in the expression, we have we can now solve for c, and c is equal to positive 9. Okay, so I'll just be leaving you the verification of solving this on your own. Okay, so since we already solved for a, for b, and c, and we can now go back to our original expression for our partial fraction and do some integration. Okay, so our a is equal to 6, so we have 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared dx. Okay, so distributing our integral and dx, so we have 6 dx over x minus dx over x plus 1 plus 9 over dx over x plus 1 square. Obviously, this is quite, at this point, this should be familiar to you, we let u equal to x plus 1 and du is equal to dx, making the substitution, the necessary substitution, and performing the solution for our basic integration, we should arrive with the solution for our integral. Now, of course, I will not be going through the details for solving for the integral. I'll just leave that to you for your own verification. Okay, so just like what I have mentioned, I'll just be presenting to you two examples for partial fraction. Although there are actually 4 cases for doing partial fraction, but I will not be covering that today. But what was covered here is simply the first case, which is you have partial fractions having distinct linear factors, and for example number 2, you have linear factors or distinct linear factors, but those linear factors could be raised to a given power. Now, case number 3 and case number 4 is when you have distinct quadratic factors. And case 4 is that you have distinct quadratic factors where possibly some of the quadratic factors in the given partial fraction has or is raised to a given power. So knowing that the only difference between these two examples that were presented in this video lecture and what I have mentioned for case number 3 and case number 4, they are somewhat similar, and the method is actually the same for expressing the partial fraction. The main difference is that for case number 3 and case number 4, where you have quadratic factors instead of linear factors, the main difference is that the expression that would appear in your numerator would not be a simple constant such as a or b, but it is actually a linear expression. So for example, now again, I'll be leaving this to you as part of the discussion in partial fraction that you will be exploring further, or perhaps I'll be reserving that discussion in another video lecture. So at the moment, I'll be just giving you a good luck on your upcoming finals.